let's see, we were on problem 15 on page 161. All right, remember we did all that god-awful arithmetic the other day, and you can, that's not the only way you can solve for acceleration either, by the way. You can solve for it the other way. Solve, set t, one of the t's equal to, and go that route, but to me it's a little easier to go this route, subtract out the tension. And so we found that our equation was going to be what? The mass times g, acceleration is equal to g times mc, dadgummit, minus mb divided by mc plus mb. Okay? And so we plug everything in. We know that's 9.8 meters per second squared times what? It was 28 minus 15 over what? 28 plus 15. And we got an acceleration of 2.96 meters per second squared. All right, now, then our next part, the next part we had to do what? It said to find the tension. Okay, well, all we have to do is go back to our equations. We had this equation, T minus MBG is equal to MA, and T minus MCG is equal to negative MA. And so we plug in A, okay? So we plug in A, T minus, let's see, the mass of the bricks was what? It says find the tension in what? What is the tension in the rope while the load is, all right, what is the tension in the rope while the load is moving? Okay, what is the tension in the rope while the load is moving? Okay, so we want to find this tension. All right, so we plug it in, and it's what? T is equal to what? MBG plus MA, and that's supposed to be a B and a C there, right? So plug everything in, and we get what? That was, what was the bricks? 15, yeah, 15 kgs, yeah, times 9.8 plus 15 kgs times 2.96, and we got a tension of, I forget what it was, 191.4. Yeah, 191.4 newtons. Okay. And then it asks what? How does this tension compare to the weight of the load of bricks? Okay, well, you just find the weight of the bricks, right? Weight is equal to M times G, so weight is equal to what? 15 times 9.8, and that was I forget what it was. How much? 147 newtons. So how does it compare? Okay, it's about what? How many times greater? About 1.3? Okay. So the tension is about, approximately, we could say, 1.3 times greater, right? Is that right? Just take the tension of the rope, divide it by the mat, the weight of the bricks. Okay. And it should be, y'all, because it's moving upwards. It's moving upwards. It should be greater. Okay. In other words, why did they ask that? They just wanted you to say, all right, just the weight of the bricks is sitting there. How much do the bricks weigh, period. Didn't ask about them moving, okay? When it starts moving, then your tension changes, okay? All right, because it's accelerating. So about 1.3 times greater. So you want to make sure that you've got a rope or a cable that's at least 200 Newton tensile strength or stronger. And actually it needs to be stronger than that, because when we look at the other side, it goes on and says what? to the weight of the counterweight. Okay, so how does the tension compare to the weight of the counterweight? When we look at the weight of the counterweight was what? 28 times 9.8, and that was what? 28 times, I didn't write it down, I just worked it out and then I did the math. 274, is that right? 274.4? And so notice then it compares what? The tension is about 1.4 times less than. Okay? All right? So it's actually about 1.4 times less than the weight of the bricks. So again, we want to make sure then our cable is actually a 300 Newton cable. The tensile strength needs to be at least 300 newtons. Does everybody see that? It needs to be at least 300 newtons. At least.
How is it less than?
Because the tension in the cable was 191.4. The weight of the counterweight, just the weight, just weight, not looking at it accelerating, was 274.4. So if you take the tension, if you take the weight of the counterweight and divide it by the tension of the cable, then we find that the tension of the cable is about 1.4 times less than the weight of the bricks. Does that make sense? Yeah, okay. So the weight of the brick, and now listen, does that make sense? Okay, which way did the bricks go? Up. Well, sure it makes sense because it's a greater weight. Okay, so yeah, that makes sense. That makes perfect sense. Okay. All right, any questions on that? All right, let me ask you this. Are there any particular ones in the end of the chapter that you would like to stop and look at? Have y'all had a chance to look at those? Now, we're going to get to the handout. But, number what? 31. Okay. All right, let me pause the video. Because I don't want to just... Okay, thank you. All right. All right, so let's draw it. All right, we defined what? What is this? Number 31, page what? 161? 2? Thank you. All right, so we have defined it as what? The sum of the forces is equal to MA. We've defined that. And remember, y'all, what the sum of forces represent? Tension, frictional force, normal force, and weight. We could put every one of those right there if we needed to. Okay. Now we draw it. This one's steep. Very steep. 55 degrees. We've got a box. Okay. And we're going to, all right, I'll tell you what let's do. Let's do the harder one first. Let's push down. You want to do that? All right. What number was this? 31. Let's push down. Okay? So we're going to push down with 120 Newton, and that's applied force. You want to look at it that way. Applied force, tensional force, whatever you want to call it. Same difference. The force is a force. All right? Now, so let's do down. We're going to do down first. All right, we've not done. We've got our normal force. We've got this, but now wait a minute, it's at an angle. Which way does gravity pull? Does the gravity pull in an angle or straight down? Straight down. That angle and that angle is the same, right? Geometry says so, right? Absolutely, it has to be. So that's 55 degrees. You want to come over here and say theta is equal to 55 degrees. That's perfect. Okay. Now that becomes what? mg? That becomes mg, doesn't it? Wait. Okay. All right, now.
So the force that's going, like, the F normal, and then the opposite force, what is that one?
Okay, we're fixing to label it. Okay. All right. Now, well, notice we're at an angle. And as Wesley has said, what are these lines here? We got to label them something. All right, we're not quite through. We've got to match this force. How are we going to find out? It's being pushed down. Well, let's see. Let's complete the right triangle. All right, now, do y'all remember what I said about vectors? I drew it a little bit too long. Well, that's pretty close to the same length. Remember what I said about vectors? As long as you keep them in the same direction and the same magnitude, you can put them anywhere you want to put them. Are those the same magnitude and the same direction? Well, we know they're in the same direction, but 120 is applied at an angle. All right, what is opposite over hypotenuse? Sine. So this vector right here becomes mg sine theta. All right, now, okay, as Wesley was pointing out, what does this vector right here become? Because how do we define frictional force? Coefficient of kinetic or static. It is mu k or mu s of what? The normal force, and the normal force is what? mg. Well, let's just hold that thought. Just hold that thought. But now, wait a minute. We're at an angle. All right, how do we define that right there? What is adjacent over hypotenuse? Adjacent, that is cosine, mg cosine theta. Well, I'll be John Dog Brown. Okay? Everybody with me? Everybody see how I'm getting that? Adjacent over hypotenuse. Hypotenuse is mg. That's cosine. Opposite over hypotenuse, sine. mg sine. Okay, very good. All right, now. Okay. Oh boy. Boy, here's where we got to be careful. All right? Notice that we're pushing down, and that mg sine theta is also pulling in the same direction. Now there's one vector we forgot to draw. This is not frictionless. So which way is friction? Okay. We know that the friction is going to be opposite direction, but how do we define frictional forces? But now remember, it's at an angle. Remember, that is the normal force. Where is our normal force here? It's what? It's not this. It is right here. And what is that value? So how do we define kinetic friction right here? Mu what?
S.
Or S. And it's moving, so it'd be kinetic. Yeah, that's okay. And it's going to be what? Not mg, but mg what? Very good. Mg cosine theta. You with me? Does everybody see that? Because remember, normal force, opposite direction. Well, hey, our opposite direction is mg cosine theta. Right there. All right. All right. Okay. All right. Now let's write an equation. And we know it's accelerating, right? Okay. All right, now, let's write an equation. So our equation is going to be what? All right, which way is mg moving? Mg sine theta. It's going this way, and notice the force applied is going in the same direction. So we're going to say force applied. Am I going to say plus or minus? Plus, because they're both going in the same direction, right? All right? Okay. Now what force is opposing me? Friction. And what is friction? mu k cosine theta is equal to what?
You know, you did cosine theta.
Yeah, I did right there. Cosine theta, yeah, mu k. Oh, dang it. Sorry. Yes, thank you. Got in a hurry. Okay? All right, thank you. All right, now, is equal to what? MA. Very good. All right. All right, now, what are we looking for? Acceleration? That's what it asked for, didn't it? Okay. Solve for acceleration. Well, look. We've got force applied plus, all right, I don't, listen, no. Everybody knows we're going to divide by m. Do I need to rewrite it? I'll go ahead and rewrite it. I'm going to go ahead and rewrite it. All right, plus mg sine theta minus mu k mg cosine theta, all divided by m, right? Oh, shoot, I didn't write the mass of the box. Y'all supposed to caught me on that. It's 10 kilograms, mass of the box, 10 kilograms. Sorry about that. Y'all got to catch me now. All right, so plug and chug now. Now, this is going down. All right, so we got what? 120 plus, going to be a lot of repetitive stuff here. 10 times what? 9.8 meter per second squared times what? Sine of 55 minus, what was the coefficient of kinetic friction? I didn't write that down either. Y'all supposed to, 0.3? Yeah, thanks. 0.3. All right, of course, that's unitless. We know that. All right, minus, and it's 0.3 times 10, I'm going to leave units off, times 9.8 times cosine of 55 degrees, all divided by 10 kilograms. And no, you cannot factor that out. Okay? All right, and we get an acceleration of, boy, it's big, 18.3 meters per second squared. All right, does that make physical sense? Okay, have y'all ever pushed something down a slope? All right, it takes off on you, doesn't it? Huh? Have you ever moved a refrigerator down a set of stairs? Dear God, don't push it. Don't push it. Because it's going to come down a whole lot faster than you want it to. Right? So make physical sense. My God, y'all, 120 newtons at a 55-degree incline? Whew, yeah, it's going to fly. It is going to move it. 18, I'm sorry, 18.3, yeah, 18.3. 18.3. That's a booking. That makes physical sense. Okay. All right, now look, y'all. What in the world do you think I'm going to do? What is going to change on my next equation when I'm pushing up? There's only one thing I'm going to have to do. Change the sign. Well, actually, though, friction is always going to be what? Opposite way. So do we mess with a friction sign? Very good. That's right. So this will become what? Yeah, that will become negative. Very good. That's exactly right. So it's the same equation. The only thing I do is flip signs on that one right there. So let's look at it. All right, everybody with me? Now watch. All right, let me redraw it real fast. All right, 55. We got the box, normal. Okay, coming down. Now it's going up. Okay, all right. Oh, excuse me. Whoa. All right. Whoops, sorry. Sorry. All right. MG is this way, so still going to be pulling that way. But now we're pushing it up in the opposite direction. We know that friction's opposite. So we got F applied. We still got, I don't need to write all that other stuff. F applied minus mg sine theta minus mu k mg cosine theta is equal to ma. Okay? And so A is equal to minus minus all divided by m. So we got 120 minus 10 times 9.8 times sine of 55. Sine, there we go. All right, minus 0.3 times 10 times 9.8 times cosine of 55, all divided by 10. Now notice what happens to acceleration. Acceleration is really low, 2.29.
What is mg sine theta? What is that? Because on the last one, we drew that because you said it was the same direction as the force applied. Wow.
Yeah. Okay, because gravity's always going to be pulling you down. Always going that way. That makes sense? See, we were pushing in the direction of gravity on that one. Now we're going in the opposite direction of gravity. The gravity's pulling down, so that means this vector's always got to be down. That makes sense? Because gravity's always going down. Yeah. Yeah. Okay. And if you think about it, if you push something down an incline, that's why we use inclines. It's a lot easier. And if you have, and they do that in business, these big warehouses, sometimes they'll have fairly light stuff. They can slide it down an incline. They use those, what do they call them? Not a conveyor belt, but it's a ramp, but it's got rollers on it, and they'll tilt it a little bit. Oh, that's easy. You can just give it a little shove, and it'll right down that thing. And that's why. Okay? It doesn't take much work at all. Inclines cut the amount of work down tremendously. Okay? It's called efficiency. Cuts it way down. It's a whole lot easier to push something up or down an incline than to have to pick it up. Because say what are we doing? Sine of 90, straight up. Sine of 90 is 1, maximum. We don't want to use maximum. We want to use less than. Okay? All right. Okay. Any questions on that? All right, are we done? Yeah. Yeah. Very good. Okay? Now that's I love these kind of problems. I love these kind of problems. And I love adding two boxes, just like you have on your handout. Oh. Okay, y'all. Then what would it be like with two boxes?
Are they touching? Are they on top?
Wouldn't matter if they're on top or touching. You just add the masses if they're on top. But if they're hooked by a rope, still the same thing, except you would do what right here? You would say, let's say I was pulling two boxes up with a rope. All right, that would be tension. All right, where are we at? Go to the next one. I'm saying pulling up. My bad. Pulling up. I'm pulling them up with a rope. So that would become tension. So we would have mg sine theta of 1 minus mu mg cosine theta of 1 minus, right, mg sine theta of 2 minus mu mg cosine theta of 2 is equal to ma. So you got 2. That makes sense? You got two boxes, two different masses. Now if the masses were the same, what could you do? Times 2 in front. That's right. Does that make sense? You got two boxes. You got to have 2 mg sine thetas and mu mg cosine thetas. Does that make sense? Because you got two boxes.
Not just add the masses together.
Let's see, your angle's the same, gravity's, yeah, you could, yeah. Let me think though, wait a minute. Yeah, you should be able to, yeah. Yeah, you could. Should be able to, yeah. You could add the masses together like do m1 plus m2 times g sine theta and m1 plus m2 times mu g cosine theta. Should be able to, yeah. Thank you, yeah. Factor it out, in other words, yeah. Very good. Factor it out. Sometimes I forget to factor, sometimes I don't. All right. Very good. Very good, very good. So you have one, I think, what number is that? number, on your handout, yeah, number 9. Number 9. So now you know how to do number 9. Okay? Right there. That's it. But it says it's asking for what? Here it gives you the acceleration, and we want to find, well, okay, instead of force applied, okay, force applied, force tension, same thing. Same thing. Remember, y'all, force is a force is tension, force is applied. Okay. Don't freak out over a symbol. We just put a T there, okay? And instead of it being equal to A, we would solve it here, wouldn't we? We'd say T and then put all that over there, right? Right? It said we got 2 masses instead of 1, okay? All right. Any other questions at the end of the chapter? What about the, shoot. Is it number 47? Yeah, let's look at number 47, because I love that problem, because I might put one like that on the test, too.
You have 2 blocks with 2 different coefficients of friction.
Then you would have to do 2 separate. Yes, you would. But, again, we look at the surface. Remember, it's the surface. We look at the coefficient of kinetic friction with the surface, yeah. Well, we could, let's see, if you had 2, yeah, let me take that back. Your surface, and then you had 2 different types of blocks, yeah, you would have to throw in the coefficients of the blocks. Yeah, that's right. Yeah, so yeah, you would have to do 2 different equations like I was talking about, yeah. But I'm not going to do that to you. That's a little bit more than we need to go. Yeah. That could happen, though. You could have like a rubber block and an acrylic block. Well, the acrylic's going to slide a whole lot easier than the rubber. Rubber's going to stick. Acrylic's going to fly. So yeah. So you'd have to put a whole lot more force. Okay. But then again, though, let's see. We're looking at it, coefficient of kinetic friction of the surface. The rubber's going to stick more, though. Yeah. Okay. But yeah, I won't do that to you. But that would be a good one to do, but I won't do that to you. All right. All right, look at 47. 47. All right, good problem right here. All right. We got a small wooden car with a mass M travels at a constant speed on the inside of a vertical track. All right, now, with a circle radius of 5 meters. So let's draw it. The radius is 5 meters. We got a car, and I'm going to draw the car right here. That's point A. The car, when it's at the bottom of the track, is equal to 2.5 mg. Now that is the normal force. So we got F of N, right? We got mg, right? And by the way, is it accelerating? It says at a constant speed. But now remember, it's going in a circle. So is it accelerating? Yeah. Yes. Because its direction is constantly changing. Okay? So that's where you got to know your concepts. Concepts of circular motion versus linear motion. Constantly changing direction still gives you acceleration even though it's constant speed. All right, now, okay. Which way is it going to accelerate? Down or up? Well, it's at the bottom of the circle. It's going to go up this way, but right now we're just looking at it here. So when we're at this point, which way is acceleration going to be? We know my velocity vector is this way, right? What did I tell you about velocity and acceleration vectors in circular motion? They are 90 degrees to each other, right? Be straight up, right? That's more of that conceptual stuff, y'all. So acceleration is straight up, right? 90 degrees to the velocity vector. Remember, acceleration and force have to be what? Now notice that also lines up with centripetal force too, don't it? Notice the normal force lines up with the what? Centripetal force, right? Well, I'll be. All right, well, keep that in mind. All right. Okay. How much time does it take for the car to complete one revolution? Holy smokes, where in the world did that question come from? Time? Now that's not tension, that's time. Okay, I'm going to write seconds right there so you don't think it's tension. That's time in seconds, period. We want to know period, not tension. That's not tension, all right? That's another one of those boo-boos with physics books. Is it temperature, time, or period, or tension? Because temperature's T too, isn't it? Oh, dear Lord. Yeah, it is. All right. Okay. All right, well, y'all, what do we got to do? We got to draw our equations, don't we? All right. We know it's accelerating, right? So the force normal is what? Force normal what? We're not there yet. It is going to be not equal to mg, but what? Force normal is always written what? It is equal to mg, but remember we're accelerating, so we got to be equals to ma. Minus, right? What? mg? Right? Right? Everybody see that? Force normal is this way, mg is that way, positive, negative, and acceleration is up, so it's positive. Okay, y'all. How much was the normal force? Well, all right, said F of n was 2.5 mg. All right, substitute that in. Now watch where we're going. Minus mg is equal to ma. So what do we wind up with, y'all? It's in 2.5. It's in the problem. It says the normal force is 2.5 times mg. It tells you that in the problem. Read that in the problem. Oh, shoot, I didn't put the problem up there. I'm sorry.
This is 45?
47. I'm sorry. I forgot to put the problem up here. I think it's right. There it is. My bad. Why didn't y'all say, hey, put the problem up there, crazy? All right, now. Okay, my bad. 2.5 mg right there. See it? My bad. Thank you. All right, now we good? All right, here we go. All right, you ready? All right, solve that, y'all. 2.5 mg minus mg is equal to ma will be what simplified? 1.5 mg. Very good. Is equal to ma, right? So, how would we find acceleration? All right, let me ask you something. Can we cancel anything out? The m's will cancel, won't they? M is m. So A becomes what? 1.5 g. All right? 1.5 g. Okay, but now we're still not done. How the heck do we get period? Come on now, let's not forget our equations. Remember chapter, was it 3? Chapter 3, we had this equation, y'all, and I put it as a concept question. I thought, man, everybody will get this because it's on their formula card. Well, everybody didn't get it. Okay, 4 pi squared r is equal to t squared. T squared is equal to what? 4 pi squared r over a. Or t is equal to what? The square root of, that's all under the radical, 4 pi squared r over what? A. Now, plug and chug, right? Yeah. So 4 times pi squared times 5 meters, that's all under the radical, times 1.5 times 9.8. You with me? So we had to do a little bit of mathematical manipulation after we determined our equations. Y'all, you always have to solve for the equations. Always. And I think that's probably another thing that bugs us about physics is like dang equations. Yeah, you got to. Okay? You got to. That's part of the conceptual parts of what we're trying to learn, these laws. Okay? Now, so what do we get? Period is equal to 3.66, right? I love problems like that right there. That's good. It's a good problem. Makes you really want to bang your head and go jump off the building, right? Well, I don't want you jumping off the building, but anyway. See, y'all, draw. Determine whether we're accelerating. Yes, we are. Normal force, weight, acceleration. Write your equation and then start doing your work. Oh yeah, I've got an equation on my formula card, acceleration for circular motion. And by the way, I should have put centripetal. Centripetal. That is centripetal acceleration. Okay? Now I could ask one like that, or I could give you the velocity and ask you to find the period. Okay? You should still be able to do it. Any questions on that?
Quick question.
Yeah.
Number 20.
No.
Number 12.
Number 12?
Yeah. Just want to make sure I understand.
Okay.
So we'll find we use, since it's accelerating, we use the sum of forces equals MA. And
Uh-huh.
So the sum of forces is at 1720, right? 1720.
That's the force of the thrust. That's F thrust, yeah.
Okay.
Mhm.
And so we'll set that equal to mass times acceleration and solve for acceleration.
Okay, but you left one thing out. What's pulling down?
Gravity.
Weight, yeah. So it'll be force thrust minus mg is equal to ma. Yeah. Yeah, don't ever forget that. You always remember you got mg pulling you down. You always have to subtract out that weight. Always. When you're going up, you always got weight in the opposite direction. Even in an angle, opposite direction. The only reason we added it a minute ago is because they were going in the same direction. But it was still going down. Did you get that? It was still going down. It's just our force applied was going in the same direction, so we add them. Okay? Okay. Does that help? Is that okay? Okay? All right. I'll tell you what let's do. Now let's really look at a good problem on here. Yeah. Everybody's worried about number 2, right? On the handout? Y'all want to do number 2 on the handout? Can y'all do number 2 without me helping you? No?
Let's try.
Try? Okay. All right. Let me hit pause on this thing because I don't want a bunch of me just this. Okay. But this is the way I work it. You don't have to work it exactly the way I do. Okay. So you draw it. Of course, we know the sum of the forces is equal to 0. It's not accelerating. It's just hanging there. Yes, gravity's acting on it, but it's not moving. It's not accelerating. All right, so we do that. This is 90 degrees. Okay, and this is what? 5 meters. It's a perfect right triangle. 4 meters. 3 meters. By the way, y'all know how to make a right triangle? Out of lumber? 6, 8, 10. 6, 8, 10. 6 foot or 6 inches, however you want to. We always did it in feet. 6 foot by 8 foot by 10 foot. That comes out to be right, doesn't it? Because what's 4 squared? No, 6 squared. 36. 8 squared, 64. 64 plus 36 is what? 100. And square root of 100 is 10. If you ever need to square something that's big in size, you need a big square. A big square. Get you some 1x4s or some 1x2s, 6 foot by 8 foot by 10 foot. Make sure you get it exactly now on the 6, 8, and 10. Nail them together good and firm, and you have a pretty doggone close to perfect square. You want good straight lumber. And then if you're like squaring a wall or something, you can put it in a corner and say, oh yeah, pull it this way, pull it that way. You got you a square. We did that a lot when I was in construction. 6, 8, and 10. Roofing, you know, pulling a straight line on a roof or something. Okay, 6, 8, 10. Okay. Or 3, 4, 5. Smaller. Okay. All right. Okay. So what's our angle? What do I use? What did I use? I don't forgot what I used. We get this angle's what? 36.9. This one's what? 53.1. That's what I got. Okay? Okay. We're hanging here, aren't we? What is that mass? 4,500? Okay. All right, now watch. You watching? You really need to do this. Make your axis. What did I always tell you? When you orient angles, you always orient them what? Counterclockwise from the positive x-axis. So this angle right here is 36.9 degrees. And what is this angle right here? Huh? Okay. If that angle's 53, then that means that angle's 53.1. So 53.1 minus 90 is what? 46 point something? 36.9. So it'll be 126.9. Does that sound right? So this angle is 126.9. Y'all, I'm telling you, this is going to make this problem flow smooth if you do this. Always orient it from the positive x-axis counterclockwise. Okay? Yeah, here we're using some geometry there. What do you call that? Opposite, what is that? Opposite, what's that? What was that theorem? Opposite, adjacent, whatever. I forgot what the theorem was, but I just know those angles are equal. All right. Yeah, all right. All right, now, all right, you know we got to do sum of the forces. Uh-oh, we've got angles, we've got angles. So do we have forces in the x and y directions? Huh? Uh-oh, what does that sound like? What's coming? Oh, me. Huh? We got a force in the x and a force in the y. So if I were to ask you to find the magnitude, you got to do what? Oh, you are smoking today. That's right. Square root of the squares. Okay, so let's do the sum of the forces in the x direction first. Since x is before y, let's do x. Common sense. So the sum of the forces in the x direction are going to be what? Well, let's label these. Since this is the one we're looking for, we're going to label this tension 1, tension 2, and tension 3, right? Since we're wanting to know what the tension is in the 3-meter cable, let's label it tension 1. You with me? You're allowed to do that. All right, now. So what do we got? So we got T1 cosine of what? 126.9 degrees. And remember, it's sum plus T2 cosine of what? 36.9 degrees plus T3. T3 is already given for us. 4,500 newtons cosine, and what is that angle right there? I didn't draw it. Ah, gummit. What is that angle right there? 270. Well, y'all, you know what that's going to be, don't you? Is equal to, is it accelerating? No. Now let's do our y's. Some of the forces in the y. Well, y'all, it's going to be the same thing except sine.
Why did you use 126.9?
Did I misadd something?
I was just wondering where.
Because you, all right, 53.1, 90 minus 53.1 is 36.9, and 36.9 plus 90 is 126.9.
Why
Or,
is that the angle each?
because you always want to orient it counterclockwise back from the positive x-axis. Yeah. Good question, all right? Okay. So T1, and you just repeat everything except change it to sine. Now again, you may have a different way you want to work it, and I don't care. And it's what? 4,500 sine of 270. And sine of 270 is going to end up being what? -1. So that 4,500 should be what? Negative. Okay. All right, y'all. We've got two equations, we have two unknowns. We can never have more equations than unknowns, right? If you're going to do something simultaneously, you can't have more unknowns than you can't have more equations than you do unknowns. Or you don't need to anyway. Okay. So what are we going to do? Okay. All right, well, the first thing we need to do before we do any substitution or anything, let's do this. Let's work out all our forces. Let's work out the numbers. So let's create our chart. So T1 cosine of 126 is going to be what? Negative 0.6 T1. So this, we're going to say T1 cosine of 126.9 degrees is equal to negative 0.6 T1. That's equal to, okay? All right, and now let's do, for cosine, what's T2 going to be? Well, T2 cosine of what? 36.9 degrees is going to be equal to what? 0.799? Now let's do the same thing for the y. T1 sine of 126.9 is equal to, well, it's just the opposite, y'all. Yeah, that's right, 36.9. And it's going to be 0.6. And that's T1 and T2. Oh, and I forgot T3. What's T3, y'all? T3 cosine of 270 is what? 0. T3 cosine of 270 is negative 4,500 newtons. All right? Okay, y'all. All right, let's now notice we've got two unknowns. Okay, so since we're solving for T1, since we got to know what the answer for the 3-meter cable is, let's take this equation right here, this one right here, and why am I doing that? Because that term is 0 and this is 0, okay? Let's solve for T2, okay? So T2 then becomes what? T2 is equal to, if you look over here at your data, T2 is equal to 0.61 divided by, and of course that's when you move everything over. Now look, let's stop and look at this. Notice that everything is equal to 0. I want to solve by T2, so that means I've got to do what? I've got to subtract from both sides. So having said and done all that, it becomes positive 0.6, right? T1 divided by 0.799. Now again, I know that was negative, y'all, but remember, we've got to do what? I've got to subtract this right here from this side to get it over here. Well, a negative times a negative is a positive. To get it on the other side of the equal sign, because we're looking for equals to. So 0.6 T1, and what does T2 become? T2 becomes 0.75 T1. Right? All right, now great. Now what can we do? We can go back and substitute that into our equations, can't we? right?
Yep.
And so we go back and substitute into our equation and solve for T1, okay? And so let's go back right here, and let's go to this equation and substitute in for T1 and solve for T1, okay? And see what you get. And I've run out of room, and I'm going to go to the next slide. So we take that equation, and actually we want to plug it in where? We want to plug it in where we've already done all the work. And so the sum of the forces and the y was what? 0.799 T1 plus 0.6 T2 minus 4,500 is equal to 0. Yeah. Uh, 0.6 T2 minus 4,500 is equal to 0. So plug it in. All right, now watch. I'm going to substitute for T2. And now what do we get? 0.75 T1? Yeah. Okay. It's kind of drawn out. And we get what? 0.779 T1 plus, what is 0.6 times 0.75? 0.45, thanks. Minus 4,500. Of course, that's newtons. All right, now we add up like terms. 0.45 plus 0.7, that's what? Plus 0.779. 779, yeah. I did write it down, right? Yeah. Sorry about that. 1.23. So we got sum of the forces into y is equal to what? 1.23 T1 minus 4,500, right? Is equal to 0. So solve for T1. T1 is what? Somebody give me an answer. T1 is,
Big number?
yeah, 1.23 is equal to 4,500 newtons. T1 is equal to what? 3,600. That sounds pretty close.
Okay, we just rounded it.
Well, okay, 4,500. All right, let's look. 4,500 divided by. Let's get an exact answer. 3658.5.
You wrote
Did I-
0.779, it's supposed to be 0.799.
Oh, I'm sorry.
Yeah,
Thank you.
so though your calculations, still good.
Okay, then what should that number be?
1.25.
Okay, thank you. Sorry about that. So then we get what? 4,500 divided by 1.25. Ah, gummit. Exactly 3,600. Good Lord, are you kidding me, Mr. Shields? Don't put one of those on the test. I'm going to put at least one. No, baloney. You can do that. Come on now. You can do that. Okay, now.
I got a question. on
Yes.
that.
Yeah, man.
How do you, when you plugged in the .75 T1,
Uh-huh.
how do you plug that in even though we found it for the X's?
Okay.
How can you plug it in if it's X and Y are the same?
Okay. Because notice that the okay. Notice that the foot. All right. Okay. Let me go back to my drawing. Okay. This equation does not have, notice this force here is 0 and that force is 0. So we want to find the tension here, okay? So once we find T, let's see, what did we do? We substituted in, we substituted in, and we found the tension. We found the substitution for T1. You go back to the Y equation because the Y equation has all three. 1, 2, 3. There's no force in the X direction. See right here? This one is 0. That one is 0. Okay? And so your forces are distributed here and also here. Okay? And so the only option we have left is to substitute here. Okay? Because this force is missing. It's gone. It's 0. Okay? So we drop down to that equation. Now, we could turn right around now and find what would the force be in the other equation or in the other tension. You can turn right around now. And notice too, does that make sense? Well, look, it's almost vertical. See, look. That is almost vertical. See, if this cable was right here, what would the tension be? 4,500. Okay? So does that make sense? Yes, it does, because it's very, very steep cable. It's almost vertical. You're going to find, however, the tension in this cable is going to be much, much lower, because look at the angle it's at. Okay? It's going to have a whole lot less tension. Okay? See, I don't have my third tension here. I can't substitute there because it's gone. It's 0. So I have to go to my Y equation. Okay? You've got 2, because remember now, tension is tension. Okay? If you got 2 unknowns, you really don't have much of a choice. Okay? To solve it simultaneously. Now, hey, you could do this. Any of y'all good with the matrices? Okay. Any of y'all good with the matrices? Matrix, doing like or finding with the determinant method. You could do it that way.
Using the bottom?
Yeah. You could find it and set it up and do a, what would that be? Would that be a 3x3 or would it be a 3x3? Or a 2x3? It'd be a 2x3, wouldn't it? Okay? Yeah. And see, what you can do now is turn right around and go back. And what you could do, look, you can do this. You can go back and substitute in. You could go back and substitute in here once you find T1 and find the X direction too. What would that be? Substitute in the tension there. Once you find the tension, what's it going to be? You see what I'm saying? You could go back and substitute in. But really, this is the only equation you have because you have all three. Okay? That's the only one you have. All right? It's the only one you have. Okay, now. Yeah. Yeah. My bad, sorry.
I just took the sine of the 53.1, which is the angle separating the vertical axis from the road we're looking for.
Yeah.
Tension. I took the sine of that and multiplied it by the total tension, which will be the 4,500 newtons, and I got 33,598.58.
3,598. That's what you got.
3,000.
So I was off by 1.4. doing it that way.
Okay. Hang on.